Welcome, everyone. I am absolutely thrilled you're joining me for today's explainer. We're going to unpack the invisible, totally silent forces that actually keep our physical world upright. Okay, let's dive into this, because literally everywhere you look, from the chair you're sitting on right now to the massive bridges you drive over, there's this profound mathematical balancing act happening right under your nose. Today, we're demystifying statics to reveal exactly how that whole shebang works. So I want you to start by just thinking about the incredibly high stakes of modern engineering. Have you ever looked up at a towering skyscraper kind of swaying in the wind, or watched one of those massive cargo ships loaded with thousands of containers and wondered what keeps these colossal structures and precarious vehicles from just, well, tipping over? It is a super delicate balance of heavy objects, and getting it wrong, well, that means absolute disaster. Think about a massive water tank. Often, they're supported by what honestly looks like a surprisingly slender frame, right? To design a structure like that, engineers can't just make a lucky guess. They absolutely have to know the exact weight of that steel tank and all the water sloshing around inside it. But here's the kicker. Just knowing the weight isn't enough. They have to know precisely where those resultant forces act in space, so they can design ground supports that won't just buckle under the pressure. Or consider an SUV navigating a seriously treacherous rocky incline. When you're driving a vehicle like this, especially if you're taking a sharp turn at high speeds, you are literally fighting physics. So, what do you think? Should the center of mass be higher or lower to make this vehicle stable and prevent it from rolling right over? If you guess lower, you hit the nail on the head. Keeping that mass low to the ground is absolutely crucial for vehicular stability. But how do we actually find that specific sweet spot? Well, that brings us to our first major concept, the center of gravity, or CG for short. In physics, the Earth exerts a gravitational pull on every single individual particle of a solid body. Imagine millions of tiny downward arrows just pulling on every single atom of an object. The center of gravity is simply the specific mathematical point where we can take all those millions of tiny arrows and simplify them into a single equivalent downward force. It is essentially the balance point for the entire system. And human movement brilliantly illustrates just how dynamic that point can be. Think about your very own body for a second. When you stand straight up, with your arms down by your sides, your center of gravity is roughly around your belly button. But the second you raise your arms up or bend over to touch your toes, your weight distribution completely changes. Your center of gravity actually shifts outside of your physical torso just to maintain your balance. It's pretty wild, right? It's abstract physics happening in your own body every single time you move. Now, closely related to the center of gravity is the centroid, but they are slightly different beasts. The centroid is strictly the geometric center of an object or area. But here is the catch. The centroid only perfectly lines up with the center of gravity if the object you're looking at is made of a completely uniform, homogeneous material. So if one side of an object is made of heavy lead and the other is light plastic, the geometric center stays exactly the same, but the actual center of gravity shifts way over toward the heavier lead. To visualize this mathematically, picture a 3D body in space. Remember those millions of tiny arrows we just talked about? An infinite number of tiny particles make up any shape, and each one has its own tiny weight. Through the magic of statics, the individual moments, or, the twisting forces, of all those particles sum up dutifully to exactly zero, right around a single point. Let's call it G. That means we can represent the entire object's weight as just one single resultant vector pointing straight down from G. But how do we find that point in complex real-world objects? Let's bring calculus out of the textbook and right onto the football field. Look at the continuous sweeping curve of a field goal post. Because of that curve, engineers can't just use basic algebra to find its balance point. They actually have to use integration, which is a totally manageable and incredibly useful tool, by the way, to calculate the total weight and pinpoint the exact center of gravity for the structure supporting it below ground. So the crucial point is that we really need a reliable system for these curved shapes, and we can actually break this seemingly complex calculus down into a really simple four-step flow. First off, you choose a tiny slice, what we call a differential element. Then you express its width, your height, figure out its exact center, and finally, you integrate. And honestly, integrating just means adding all those tiny little slices together across the whole shape. Visually, it's brilliant. Whenever you see an integral symbol in engineering, I want you to just imagine slicing an irregular shape into a million tiny, perfectly rectangular pieces. We all know how to find the center of a simple rectangle, right? So by slicing the big shape up, finding the center of each individual slice, and adding them all together, we can easily find the precise center of even the weirdest, most irregular, continuous areas. Now, what's truly fascinating here is how geometry dictates these rules. We've done the integration for standard shapes so many times that they're basically just known formulas now. Like a basic triangle centroid is always exactly 1/3 of the way from its base. Simple. But think about a quarter circle or a half parabola. The curves actually push the center of area to very specific mathematical coordinates, dictated entirely by the symmetry and geometry of the object itself. But hey, let's transition from pure math back to practical engineering for a second. What happens when you aren't dealing with a single continuous curve, but a massive composite shape made of dozens of different pieces? Think about a crane lifting a giant concrete bridge segment. It's got hollow sections, varying thicknesses, steel rebar inside, the whole works. How on earth do we find the balance point so the crane doesn't tip and just drop tons of concrete?
Well, we treat it like a giant puzzle. Consider an industrial compressor assembly, for example. It's made of a bunch of distinct parts. There's an instrument panel, a liquid storage unit, a super heavy filter system, and a piping assembly, all sitting together on a structural framework. If we know the individual weight and center of gravity for each of these separate components, how do we combine them to find the true center of the entire assembled machine?
We use what I like to call a structured treasure hunt. We build a table. This is known as the composite method, and it is just beautifully organized. We swiftly list out all our known pieces in one column, toss their weights in the next, and track their moment arms, which are basically their individual distances from our starting axis, in the third. The real magic here isn't the table itself, it's the fact that by dividing a complex machine into these simple, known pieces, the once daunting math becomes incredibly straightforward. And here is the triumphant final step. Once our table is full, we literally just sum up the columns. We multiply each part's distance by its weight, add all those together, and then divide by the total weight of the entire machine. That simple division formula pinpoints the exact x, y, and z coordinates for the center of gravity of the whole complex assembly. Boom. No advanced calculus required, just some good old-fashioned organization and arithmetic.
Let's move on and see how this builds, because once we find the center of an object, a whole new mystery emerges. Finding the balance point is great for knowing if something will tip over, right? But what about its actual strength? Think about a heavy steel I-beam compared to a wooden T-beam. We can find their centroids easily enough, but how do engineers know if these specific structural shapes are actually going to resist bending under heavy loads?
That introduces the critical next level of structural analysis, the moment of inertia. Also known as the second moment of area, this concept goes way, way beyond just finding an object's balance point. When a beam is subjected to weight, it naturally wants to bend. The moment of inertia mathematically represents how the area of that beam is distributed away from its center to resist that bending. It's actually a lot like a tightrope walker holding a really long pole to stay steady. Let's clearly compare these two pillars of statics side by side so you have this locked in. The centroid is all about location. It pinpoints the exact geometric center or balance point of an area. The moment of inertia, however, is all about structural strength. It measures how that area is spread out. An I-beam is strong, not because it has a ton of solid material in the middle, but because its material is distributed as far away from its centroid as possible, which maximizes its moment of inertia to resist the flexion. I want to leave you with this final, kind of provocative thought. Take a second and literally look at the room around you right now. Look at the ceiling, the walls, the door frames. Where's the center of gravity of the architecture holding up your roof? How are those invisible forces balancing the moment of inertia in the beams above your head? Once you truly understand statics, you can't help but look at buildings, bridges, and vehicles with a newfound awe for the invisible math that is keeping you safe every single day. Thanks so much for joining me on this explainer, and hey, keep questioning the world around you.